Hello students, welcome to this new video presentation on oscillations which is given in chapter number 14 of class 11 physics. The study of oscillatory motion is basic to physics. Its concepts are required for understanding many physical phenomena. Here the object moves to and fro about a mean position. An example of such a motion is a pendulum of a clock. Similar examples are there like cradle for children and swinging on a swing, etc., etc. The description of periodic motion in general and oscillatory motion in particular requires some fundamental concepts like period, frequency, displacement, and amplitude and phase. All this we'll study in today's lesson. Here we'll study. First, I will introduce the topic, followed by period discussions on periodic and oscillatory motion, simple harmonic motion and uniform circular motion, velocity and acceleration in simple harmonic motion, and finally we'll end today's session with discussions on force law for simple harmonic motion. This topic is very important. Please note down all the important points which will help you in your examination. I welcome you once again. Periodic and oscillatory motion. A motion which repeats itself over and over again after a regular interval of time is called a periodic motion. Please see the figure on the screen which has given three examples of a periodic motion. Figure A shows a sawtooth wave which can be compared to the path traced by an insect which climbs up a ramp and falls down. Figure B can be compared to a path followed by a child while climbing up the stairs. The child initially goes up and comes down and repeats the process identically. Its height above the ground would look like that in figure B. The third example is that of a person playing the game of bouncing ball off the ground between his palm and the ground, and its height versus time graph would look like the figure C. Thus, a motion which repeats itself over and again after a regular interval of time is called a periodic motion. In all the three examples, capital T is plotted on the x-axis. That is, x-axis is t and y is the amplitude or the distance. So here capital T is called the periodic interval, regular periodic interval. There is another type of motion which is called oscillatory or vibratory motion. A oscillatory or vibratory motion is that motion in which the body moves to and fro and or back and forth repeatedly about a fixed point in a definite interval of time. Oscillatory motion is called the harmonic motion. Please see the figure 2, that is a white background, wherein the spring is fixed to a rigid wall. At the other end of the spring, a block is attached. The initial position of the block without applying any force is called in equilibrium position or mean position. Whenever we apply the force, we can either pull the block on the right hand side or we can push the block on the left hand side. That means the block is displaced. But in all these cases, the block goes to and fro repeatedly over a fixed point of time or over a definite interval of time. Such motions are called the harmonic motions. Another example is that of a pendulum of a clock. An oscillating simple pendulum, its motion can be described in terms of an angular displacement. This is angular displacement represented by an angle theta. You can mark it as a theta. And it is displaced either to point A on the left hand side or displaced to point B on the right hand side, just inscribing an angle theta. Hence, the motion of a pendulum of a wall clock is also an example of an oscillatory or vibratory motion. Harmonic oscillation is that oscillation which can be expressed in terms of a single harmonic function. That is, the motion of a body can be expressed in terms of a single harmonic function given by the relation y is equal to a sin omega t. If the motion is in the x-axis as shown in the middle figure, it will be x is equal to x a into sin omega t, or it can be, if it is a vertical motion, it can even be expressed by a relation y is equal to a cos omega t. That means harmonic oscillations can be expressed as a sin omega t or y or a cos omega t. Non-harmonic motion is that oscillation which cannot be expressed in terms of a single harmonic function. That is, for example, non-harmonic motion is given by the trigonometric relation y is equal to a sin omega t plus b sin 2 omega t or sin squared omega t. So these are non-harmonic oscillations. Period and frequency of a harmonic motion. We know that any motion which repeats itself at regular intervals of time is called a periodic motion. The smallest interval of time after which the motion is repeated is called its period, and it is denoted by the symbol capital T. Its SI unit is second. Thus, the time period capital T of a particle executing simple harmonic motion is the time taken to complete one cycle. It is the least interval of time after which the periodic motion of a body repeats itself. The SI unit of time period T is second. The next important physical parameter is frequency. It is represented by letter nu, Greek letter nu. Sometimes in some of the books they represent frequency as f, small letter f. Frequency is the reciprocal of the time period capital T. Thus, the reciprocal of capital T gives the number of repetitions that occur per unit time. This quantity is called the frequency of periodic motion. It is represented by the symbol nu, Greek letter nu. It is defined as the number of periodic motions executed by body per second. Thus, nu is equal to 1 over t, that is the reciprocal of the time period t. The unit of nu is per second. It's because t is in the denominator. Hence, the unit of nu is per second. The SI unit of frequency is Hertz. Hertz, H-E-R-T-Z. It is named after the discoverer Heinrich Rudolf Hertz, the discoverer of radio waves. 1 Hertz is equal to 1 oscillation per second. That is equal to 1 into s to the power of minus 1. The next physical parameter is the angular frequency omega. It is a scalar measure of rotational rate, that is rate of rotation. It refers to the angular displacement per unit time or rate of change of phase or phase of a sinusoidal waveform, or at the rate of change of the argument, that is argument of the sine function. This about the angular frequency we will study in detail in the next slide. So just remember that omega is equal to 2 pi by t. That is, it is angular. When we talk of angular frequency omega, we have to multiply it by 2 pi into 1 over t. The SI unit of angular frequency is radians per second. Since frequency of oscillation is 1 by t, Omega is 2 pi times the frequency of oscillations. Displacement. Displacement is the deviation from the mean position. The displacement can be represented by a mathematical function of time. In case of periodic motion, this function is periodic in time. One of the simplest periodic function is given by the relation f of t is equal to a into cos omega t. Let it be equation 1a. If the argument, that is the angle omega t, is increased by an integral multiple of 2 pi radians, the value of the function remains same. The function f of t is then periodic and its period capital T is given by the relation t is equal to 2 pi divided by omega. This relationship equation is shown in the figure on the screen. Please see here the amplitude varies between plus a to minus a and its period is capital T. The amplitude. Amplitude of a particle executing simple harmonic motion is maximum displacement on either side of mean position. In the graph, please see the OT along the x-axis represents the time and the magnitude or the amplitude is represented on the y-axis. The mean position is along the x-axis and the amplitude varies maximum and minimum across the mean position. Thus, amplitude of a particle executing simple harmonic motion is its maximum displacement plus a or minus a on the either side of the mean position. A is the capital A is the amplitude of the particle. If the mean position is at origin, the position, that is x coordinate, depends on the time in general, as we can write it as a sine function also, as that is x of t is equal to capital A into sine omega t plus phi. Here at the mean position x is equal to 0. Therefore at extremes, that is at the plus maximum and negative maximum is the amplitude is plus a and minus a. If omega t is increased by a multiple of 2 pi radians, the value of the function remains same. Then the period capital T is equal to 2 pi divided by omega. Let it be equation 1b. Thus, we can write the function stated in 1a as f of t is equal to f of t plus capital T. Let it be equation 1c. This is also a periodic function with the same period capital T. The same result is true for sine function. We can either represent it as a f of function of a cos omega t or f of t is equal to a sin omega t. Let it be equation 1d. Now we will consider the combination of sine and cosine function, wherein we combine two periodic functions. Consider a function, a trigonometric function f of t is equal to a sin omega t plus b cos omega t. Let it be equation 2a. Then this is also a periodic function with the same period, because omega t is same for both the terms on the right hand side. If we put a equals d cos phi and b equals d sin phi in equation 2a, then we can get this. We can simplify equation 2a as f of t is equal to d into sine of omega t plus phi, using our standard trigonometric relations. So f of t for two functions will be f of t equals capital D into sine of omega t plus phi. See, the term in the bracket is the argument. The combination of two functions, that is sine and cosine function, is shown in the figure on the right hand side. So here the A is f of t is equal to A of cos sine omega t is shown in the blue line, and f of t is equal to b cos omega t is shown on the figure on the figure number 2, that is a plot of displacement as a function of time as obtained from the equation 1a is with phi is equal to 0. The curves 1 and 2 are for two different amplitudes A and B. So the second curve, black color, varies between plus B and minus B, whereas blue colored wave varies between, oscillates between plus A and minus A. The combination of these two can be represented by the function f of t is equal to d into sine of omega t plus phi. Here d and phi are the constants given by the relation d is equal to square root of a square plus b square, and phi is equal to tan inverse of b by a. Thus, any periodic function can be expressed as a superposition of sine and cosine functions of different time periods with suitable coefficients. Phase and phase difference. While the amplitude A is fixed for a given simple harmonic motion, the state of motion, position and velocity of the particle at any time t is determined by the argument omega t plus phi in the cosine function. This time dependent quantity, that is omega t plus phi, is called the phase of the motion. Let us repeat it. Phase. Phase is a physical quantity which completely expresses the position and direction of motion of the particle at any instant with respect to its mean position. In equation, x of t is equal to a sin theta, which can also be written as a sin omega t plus phi. The argument omega t plus phi is called the phase of the motion. The value of phase at t equal to 0, suppose in this term, in this equation, omega t plus phi, if you put t equal to 0 in omega t plus phi, then phi is called the phase constant or phase angle. If the amplitude is known, phi can be determined from the displacement at t equal to 0. Two simple harmonics motions may have the same amplitude A and omega but different phase angle as shown in figure B. Phase difference. If two particles perform simple harmonic motion and their equations are represented by x1 of t is equal to a sin omega t plus phi 1 and x2 t as a sin omega t plus phi 2, then delta phi, that is the phase difference, is the delta phi equals omega t plus phi 2 minus omega t plus phi 1. So subtracting, we get omega t gets cancelled, phi 2 minus phi 1. Phi 2 minus phi 1 is the phase difference. The figure on the screen, the second figure on the screen, shows a plot of displacement as a function of time. The curves 3 and 4, 3 that is blue colored and 4 are for phi is equal to 0. Phi is equal to 0 and minus pi by 4 respectively. For this blue colored line, phi equals 0 and for the black colored it is pi by 4, because you see here at 0 maximum is capital A for blue line, whereas this is less than A. That is why it is lagging by pi by 4. This distance is pi by 4. The amplitude is same for both the cases. So amplitude is same, but phase phase is changing. The figure 3 on the right hand side depicts the plot for phi is equal to 0 for different periods. Here the blue color line wave has different period, has a larger period, whereas the black colored wave has got lesser period. So this depicts the plot of equation A sin omega t plus phi for two different curves. Simple harmonic motion. Simple harmonic motion is a specific type of oscillatory motion in which a particle moves in one dimension. The second condition is the particle moves to and fro about a fixed mean position where the net force is 0. Another condition is the net force on the particle is always directed towards the mean position. And the final condition is the magnitude of the net force is always proportional to the displacement of particle from the mean position at that point. That is, F net is proportional to x. So removing the proportionality constant, we can write F net is equal to minus k into x, because the direction of the force is always directed towards the mean position. So we can write this equation, that is F net equal to minus kx, as F substituting force is mass into acceleration. Therefore the left hand side is ma equals minus k into x. Therefore, rearranging, A is equal to minus k by m into x. Therefore, we can substitute minus k by m as omega square, where omega is the angular frequency and equal to square root of k by m. We also know that acceleration is the second order differential, which can be written as d squared x by dt square, where x is the displacement. So this is second order differential of the displacement. D squared by dt square is equal to minus omega square x. This equation is called the differential equation of simple harmonic motion. The general expression for xt satisfying the equation, that is d square x by dt square plus omega square x equal to 0, is x of t is equal to a sin omega t plus phi, where a is the amplitude. So the details about this equation are given in the insert box. Here please note, we can write x of t as a sin omega t plus phi, or x of t equals a into cos omega t plus phi. Therefore, the simple equation for simple harmonic motion can be written as x of t is equal to a into cos omega t plus phi. Here x of t is the displacement x as a function of time. A is the amplitude, omega is the angular frequency, and omega t plus phi is the phase or the time dependent, phase time dependent. Please see here, small t is there, that is why it is time dependent, and phi is the phase constant. Now we will draw the correlation between simple harmonic motion and uniform circular motion. In this section, we will show that the projection of uniform circular motion on a diameter of the circle follows a simple harmonic motion. Consider a particle P shown on the screen moving uniformly on a circle of radius capital A. This radius OP is capital A with angular speed omega in anticlockwise direction. Please see that particle is moving in the anticlockwise direction. The initial position vector OP at t equal to 0 makes an angle phi with the positive direction of the x-axis. This is the positive direction of x-axis and it makes an angle phi with the x-axis. OP makes an angle phi with the x-axis. In time t, it will cover a further angle omega t and its position vector will make an angle of omega t plus phi with the positive axis. Next, consider the projection of OP on the x-axis. So this will be OP dash. See, this is the OP and its projection on XC is plotted as OP dash as shown in the figure. The position of P dash on x-axis as the particle moves on the circle is given by the relation x of t is equal to a into cos of omega t plus phi, which is defining equation of simple harmonic motion. The position of P dash, position of P dash which moves to and fro on the positive x-axis is given by the relation x is equal to a cos omega t plus phi, which is defining the equation of simple harmonic motion. This shows that if P moves uniformly on the circle, this is P is moving here, but its projection is OP dash. It is moving x-axis on the diameter of P dash. Its projection P dash on the diameter of the circle executes a simple harmonic motion. So P dash executes a simple harmonic motion of a particle P which is moving on a circle. The particle P and the circle on which it moves are referred to as the reference particle. So P is called the reference particle and this circle on which the P is moving is called the reference circle. We can take projection of P on any diameter, say y-axis. Say for example, in this case we have taken projection of P on the x-axis. Similarly, we can take projection of P on the y-axis. In that case, yt, that is y function of t of P dash on y-axis is given by the relationship y is equal to a sine omega t plus phi. This is also y equals a sine omega t plus phi is also a simple harmonic motion of the same amplitude because capital A is common for both the equations as that of the projection of on the x-axis but differing by pi by 2. Please note here the phase difference between P dash, that is projection on x-axis, and the projection on the y-axis, that is x is equal to a cos omega t plus phi and y is equal to a sin omega t plus phi, is the phase difference is pi by 2, that is 90 degrees. In spite of this connection between the circular motion and simple harmonic motion, the force acting on a particle in linear simple harmonic motion is very different from centripetal force needed to keep the particle in uniform circular motion. Please note, in spite of the correlation, the relationship between the uniform circular motion, that is centripetal force, and the force in simple harmonic motion is totally different, is very different. Velocity and acceleration in simple harmonic motion. In this section, we will derive equations for velocity, acceleration, and also we will explain using graphical representation of all these physical quantities: displacement, velocity, and acceleration. Let us start with displacement. We know that the equation for displacement is given by the mathematical equation y of t is equal to capital A into sine omega t plus phi, where yt is the function of displacement, function of time, capital A is the amplitude, omega is the angular frequency, and phi is the phase constant. Let it be equation 1. We can obtain the equation of velocity by differentiating the displacement, that is v is equal to dy by dt. Therefore, v is equal to dy by dt, and substituting the value of y from equation 1, we get v is equal to d by dt of a into sine omega t plus phi. So, differentiating from the knowledge of differential calculus, we know that v of t is equal to a into omega into cos omega t plus phi. That is, a we have taken outside. D by dt of sine omega t is cos omega t, omega into cos omega t plus phi. Let it be equation 2. We also know that the acceleration is given by differential representation of differentiation of velocity, that is acceleration represented by a of t is dv by dt. So in this equation you substitute the value of v of t from equation 2. Thus we can write acceleration a of t as d by dt of a omega into cos omega t plus phi. Here we have substituted the value of v of t from equation 2. So now differentiating, we get a of t is equal to a omega into omega square sine omega t plus phi. This is the equation for acceleration. Therefore, acceleration can also be written as omega square, keeping omega square and substituting for a sine omega t plus phi as y of t, that is from equation 1, we get a of t is equal to minus omega square into y of t. Let it be equation 3. Now all these three equations, that is equation 1, equation 2 and equation 3, are plotted in the graph sheet shown on the screen. The topmost is the displacement. We know that the equation for displacement is given by y of t is equal to a of sine omega t. Here we have treated the phase constant phi as 0. Therefore, the plot is shown here. It has got a maximum. The amplitude is plus a to minus a, and it is a time. T is the time period. So y of t is plus a to minus a, and in between the maximum value is plus a and minus a, and the minimum value is 0. Similarly, plotting the velocity, that is time is on x-axis represented by 0, capital T and 2t and other time periods. Velocity, we have derived the equation as velocity v of t is equal to a omega into cos omega t. Therefore, plotting we get, because sine has changed to cos, there will be a phase difference of 90 degrees, pi by 2. Hence, the maximum amplitude is plus AW and minimum amplitude is 0, and it fluctuates between plus a omega to minus a omega, and the plot is shown here. And the acceleration equation, whose equation is given by a of t is equal to minus a into omega square sine omega t. That is from equation 3. That the plot is shown here. Please see the phase difference here between displacement, velocity and acceleration. Please note it and draw the graph yourself. So summarizing, we get all the three quantities, displacement, velocity and acceleration, show harmonic variation with time having the same period. So the period is same, that is omega t plus phi. The velocity amplitude is omega times the displacement amplitude. Therefore, velocity is multiplied by omega into a cos omega t. Hence, velocity amplitude is omega times the displacement amplitude. The acceleration amplitude is omega square times the displacement amplitude. Please see here and note from the equation 3. In simple harmonic motion, velocity is ahead of displacement by an angle pi by 2. See here, velocity is ahead of displacement by an angle pi by 2. Similarly, acceleration is ahead of velocity by an angle pi by 2. Here you see the phase difference between velocity and acceleration is pi by 2. You see the here 0, here 0, and it is the difference, phase difference is pi by 2. The acceleration is ahead of displacement by an angle, phase angle pi. Please see here. Here it is positive, and whereas the acceleration is negative. So therefore, there is a phase difference of pi. Summarizing the physical quantities, displacement y of t is given by a sin omega t, neglecting the value of phase constant as 0, that is treating phi is equal to 0. So the minimum value is 0 here. For displacement, minimum value is 0 and maximum is plus a and minus a, plus or minus a, and velocity is given by a omega cos omega t plus phi. Phi is 0. Therefore, the maximum is a omega. Please see here, it is maximum is a omega plus minus a omega and minimum is 0 here. That is the mean position, it is 0. Finally, acceleration a of t is equal to a omega square sin omega t from the equation 3, and here also the minimum is 0 and maximum is omega square into a. Some more derivations can also be obtained. We know that v of t is equal to a omega cos omega t from the equation 2. Therefore, we can write cos omega t as square root of 1 minus sin square omega t. That is from the knowledge of trigonometric angle, trigonometric ratios. Therefore, v of t is equal to a omega into square root of 1 minus sin square omega t. Therefore, we can put the values as sin square omega t is equal to y square by a, that is from equation 1. Therefore, substituting for in equation y, we get v of t is equal to omega into square root of a square minus b square. Force law for simple harmonic motion. We know that the Newton's second law of motion gives the relationship between force and mass and acceleration. That is, force is equal to mass into acceleration. In simple harmonic motion, force is proportional to the displacement. That is, f of t is equal to minus k into x, where f is the force, k is a force constant, and x is the displacement. Let it be equation 1. Therefore, substituting for force from Newton's second law of motion, We know F is equal to MA. So we can write F as M into A and the right hand side of equation as it is. Therefore, MA is equal to minus K into X. Or rearranging, we get A is equal to minus K by M into X. Let it be equation 2A. We also know by the relationships in simple harmonic motion, A is equal to minus omega squared X. That is the relationship derivation derived from displacement velocity. Therefore, A is equal to minus omega squared X. Substituting this value, we can get minus K by mx is equal to minus omega squared X. Let it be equation 2b. Therefore, from this equation in 2b, xx gets cancelled. Omega is equal to square root of k by m. A minus and minus negative sign also gets cancelled. Let it be equation 2c. So, like acceleration, force is also directed towards the mean position. Hence, it is sometimes called the restoring force in simple harmonic motion. To summarize the discussions so far, simple harmonic motion can be defined in two ways. Either by using equation x of t is equal to a of cos omega t plus phi. That is, the displacement is equal to amplitude into cosine of the angle argument omega t plus phi for displacement, or by applying force is equal to minus kx into t, x of t, that is equation 1 above, that gives its force law. Going from equation of displacement to the equation of acceleration required us to differentiate two times. That is, using this equation x of t is equal to a cos omega t plus phi, we have to differentiate two times to get the equation for acceleration. Likewise, we can obtain the value of x by integrating force. That is, force is equal to minus k of x. That is, two times we have to integrate this equation 1. We can get back x of t is equal to a of cos omega t plus phi. Note that the force in equation 1 is linearly proportional to x. A particle oscillating under such a force is therefore called a linear harmonic oscillator. In real world, the force may contain additional terms proportional to square of x or cube of x, that is x square or x cube, etc. Then these are called non-linear oscillators. With this, we will end this lecture, and in the next lecture we will take up oscillations and continue with part 2. Till then, goodbye.